All right, this is Vectors Day 4, and today you learn a whole lot of stuff because yesterday you just learned the basics that we can use for all the rest of it. And yesterday's was that if I told you like 1, 4, 7, you should be able to picture that in 3D space. Okay, or if I say column vector 2, 6, that's much easier because it's not 3D. Everybody just draw me column vector 2, 6. I'm putting it in column vector form. It's got a 2 on top, a 6 on the bottom, and you should be able to draw me an arrow that looks like that. If you're smart, you can probably draw it at the origin, with its tail end on the origin. All right. These are confusing. I really like having people have a partner to ask when they're like, I don't get what he's talking about. All right, so I'm going to pause for a second. Okay, so hopefully by now you've figured out that 2, 6 just means it's almost like you added a couple of vectors to get this vector, but there it is. Do you get it's kind of like I added a couple vectors this way, plus a whole bunch of little mini vectors that way? That's kind of what I was doing when I was getting that vector 2, 6, is adding a couple vectors that go this way, which is 2 I vectors, and 1, 2, 3, 4, 5, 6 j vectors. And if the thing came out of the board towards you, first of all, if that actually happens, you should run away because there's probably some sort of science fiction involved. But if you imagine that it comes out towards you, that would be the that would be the k direction if it was coming out towards you. All right, so this is the vector when I say 2, 6 like this, it's that blue vector right there. Okay, what you learned yesterday was how easy it was to add a couple of vectors when they're in column form. You don't have to draw pretty pictures and everything. Let's just say that we had the vector 5, negative 1. You do not have to draw it. I just want to know what happens when I add vector 2, 6 to the vector 5, negative 1. Don't overthink this. Tell me what the answer is, then draw it. I'm going to pause for a second while you try that. Okay, I think you could teach third graders to do this part. 2 plus the 5 makes 7, and 6 plus the negative 1, although I'm not sure they can handle the adding positive and negative integers part, but anyway, it would be 5. Did you get 7, 5? Raise your hand if you did. Good. And I hope pictorially it actually made sense too. If I draw 5, negative 1, it would have looked something like that, over 5 and down 1. And then I grab it and I bring it up here, and then my final answer is supposed to be 7, 5. Does that seem reasonable? That could be like about 7 and about 5 right there. That final one, I'll make dark blue, would be your, what's that king called again? Let's start with an R. That's called the resultant. All right, good. All right, so that's what you learned yesterday, and you got to at least imagine that if it was 3, 2, negative 5, that could be over 3, up 2, but then the way we were saying it was kind of away from us in this case because it's negative, away from us 5, and then it would connect the origin to that spot that was way back there somewhere. Really hard to draw on the board in 3D. So what we do is we draw a box like this. Everybody go to this slide, and that gives you the feeling of 3D. Okay? Now I kind of have a bone to pick with where they put the origin here, because to me, it feels like when I move into this cube that I'm got a negative direction. But I'm going to just say it this way. The way they have designed this, and they can label it any way they want to, right? They have labeled this as a cube, which is a real thing in the real world that has edge length 5. That means none of those sides there in the first place from the beginning, none of these sides can be negative. So if you move this way, that must be positive. If you move that way, it must be positive. And if you move that way, it must be positive. Okay? So and they have also labeled it with I. This one's J, and this one's K direction. So you got to think of it as the X and the Y axis. It's almost like this is a table here. and the x and the y-axis are laying on the table, and the k is coming up off the table. So it's like x, y, z, and the x and the y are kind of like this and this, and then the z is coming up off the table. All right, so the question becomes, if you wanted to name ray OG as a column vector or a position vector, would you please write it both ways? How far over, how far up, how far out? Remember, I is this way, J is this way, K is that way. And don't overthink this. This is not meant to be super hard. Column vector would be written kind of this way. A position vector would be written kind of that way, except you need your numbers in there. Since this is on the edge of a cube, that means we can move 5 in every direction. Did you get 5, 5, 5? Raise your hand if you did. You were right. Okay, so that's the answer for the first one. But the answer for the second one is tougher because it doesn't have its tail at the origin. I'd like you to think through BD, which goes from here to here, and here's my hint for you. You can either move it in your mind, move the vector so that it's got its tail at the origin, which will tell you, ooh, there's at least one negative number involved here. Or, I kind of like this better, you can take the origin and move the origin to it. You see what I'm saying? All right. Try to figure out, maybe there's a 0 involved, maybe there's a negative number involved. Try to figure out what BD is in column vector or position vector form. And then try EB, and that's a different situation. I'll pause while you try to do those two. Okay, let's see how you did. If you move this over here, I hope your first step is to think, okay, which one's X? Which one's kind of like X? This one's kind of like X. That means this one's kind of like the X, which is I. This one's kind of like the Y, which is J. And this one's kind of like the K, I, J, K. Or if you use X, Y, Z, it's kind of like the Z. So I'm going to label these as I, J, and K directions. It went negative in the I direction. Did you get negative 5I? Raise your hand if you did. Awesome. Then, do you get in the J direction? It did not move at all in the J direction. So 0J, or you just don't even put J. And then 5K. Raise your hand if you had that one right. Good. And then the last one was 5I plus 5J minus 5K. All right. So, now we got to jump to another type of problem. This one really can be confusing, but if you think of it as these two are vectors, which is 3, 5, and what's this one? This vector v here, 1, negative 2, and they're adding the vectors, right? You know how to do that, right? And then they're timesing them by a. They don't tell you what a is. But there's timesing by something. Do you get they could add the vectors, you get this new vector, and you times it by, I don't know, like 6 or something? We're timesing it by something, A. All right. I'd like to help you by, I showed you again already that they're adding these two vectors, and here's the two vectors. So try to clean this up and figure out what A and B have to be. I personally would use a system of equations, but a lot of kids use guess and check, and they actually were able to figure it out. But if you get it with guess and check, then go back and try to figure out how you could have done it if the numbers hadn't been nice. The numbers are nice, you know, like 10 and 2 or whatever. But you have to figure out how you could have solved this if it hadn't been nice numbers. That's the challenge for this one. I'll pause for a second. Let me do that. Hopefully you started by adding these two together. It's this simple. 4 and 5 and negative 2 makes 3. Do you agree it's 4, 3? Okay, next we have a times that equals 8i plus b minus 2 times j. Well, it'd be nice if this had i's and j's in it, wouldn't it? So that it was all i's and j's. So, what's 4 over 3 really? 4i plus 3j. Okay, so then, to get the I part of my answer, do you get, I'm going to take A times the 4I, A times the 4I will equal the 8I. That's the I part of my answer. Can you see that A therefore must be 2? Raise your hand if you got A equals 2. Good. That's mathematical. It wasn't just guessing and checking. I can divide by 4I on both sides. And I will get 8i divided by 4i, which is 2. Cool. If I know A is 2 then I can go like this. 2 times the 3j has to equal b minus 2j. 2 times 3j will be 6j, has to equal b minus 2 times j. And can't I solve that for b then? Yeah. 6j equals b, I'm going to call it jb, minus 2j. Okay. And I just distributed out my j there. And now I got j's in everything. Well, if I could factor out that j, it'd be pretty handy. I know. You can just go, oh, I know b is 8. But yeah, I think I maybe just do that. Look, that's got to equal that, right? So therefore, b must be 8. Yes. Okay. Okay. So I agree with you. I put this in vector form. Now, I talked about that last hour, and we didn't actually do it. I suggested we could. So I take it you did it that way, and it was nice. So tell me what this right side turns into, as I now have 2 over 4, 3, equaling, what's this?
A over b minus 2.
8 over b minus 2. Awesome. And now, you're right, much cleaner. All right, I like that a lot better. So, obviously, 2 times the 4 makes the 8. 2 times the 3 makes b minus 2. 2 times 3 makes b minus 2. Add 2 to both sides. 6 plus the 2 equals the b. B must equal 8. Okay. So I think the moral of the story was, in this case, put them in column vectors was probably the way to go. All right. I chose to put them all in i's and j's, and it worked, but it was definitely more clunky. Now, what? You know why columns is better? Because it takes out the I and the J. You don't have to worry about I's or J's at all. So I agree with you 100%. I just kind of fell into what we did last hour, and I had mentioned that was a possible way to do it there. All right, enough about that. Enough about yesterday. We got to get to the new stuff now. And here is kind of the big picture of what we are trying to solve. If I have this vector 5, negative 3, do you get that generally would look like that arrow right there? Does that seem like 5, negative 3 to you? About? All right. So I'm going to call that vector A. And vector B is negative 2, 1. Negative 2, 1. Now, again, it's hard to get perspective. Just know that this is not a straight line that's like that. I wish these had a better, bigger angle between them, but it's the angle right there is some angle. To get in 3D space, I'm doing this in my room so people at home can't see it, but in 3D space, they can be even more of a a challenge to see. You can see the angle between it because I'm holding up two sticks here. But do you get the angle between two vectors can be a challenge to visualize? All right. It's not that hard when I hold up the sticks, but if I just don't have the sticks there and say, what's the angle between those two vectors, it's hard to picture even. All right. There's a formula for the angle between two vectors. And that's the main thing I need to teach you today. But I need to teach you a bunch of other things. I got to show you like why I need to teach you this stuff. Here's the formula for that we're going to use to find the angle between two vectors. And it involves a bunch of things that you don't know. I know you know how to find cosine of an angle. That's the angle between the vectors. That part is the easy part. And if I knew all the other parts, if I knew what this number was times that number, you can multiply two numbers pretty easy. But what are those things in bars again? Yeah, but they're not really absolute values. They strip off the what? They strip off the direction, so it leaves the magnitude. Those stand for the magnitude of A and the magnitude of B. We got to get good at finding those magnitudes, so I can just say, okay, the vector's 6 comma negative 2. And you can go, oh, so the magnitude is blah. You got to be able to say it really quick and easy. Okay, so I got to show you how to do magnitudes well. And then you got to be able to do a dot product. And the dot product is actually super easy. But the weird thing about it is that you can't actually draw the dot product. It's just a number that you use. And you can't like show you, oh, it's the distance between the vectors or something like that. It doesn't exist. Is there a precedent for that? Yeah. Imaginary numbers, when we graphed them, you could never see the roots that were imaginary. You just had to know that they were there. Okay? Same idea here. A dot product. That is a dot product of two vectors. It's a number that you can't see in the graph. All right, so big picture, I got to teach you dot product, and I got to teach you magnitudes. And I think you kind of know the magnitude thing already. I just got to kind of tune it up a little bit. All right, so imagine for a moment I had this vector. Could you shut the door for us? Or actually, it's easy to get out. Shut the door for us, please, because there's people talking out there. All right, let's go with 8, 2. Could you buy that vector is 8, 2? Okay. Do you get when I ask for the magnitude, it's really finding the hypotenuse? Does that make sense to you? So really, it's just the square root of, remember me saying at the beginning of the year, I didn't want you to write out a squared plus b squared equals c squared, always find these things. You just jump right to square root of the other ones squared, which are 64 and 4, and what should I do with them? Add them. Square root of 64 plus 4, so the square root of 72. You get how I can find the magnitude of this vector really quick by just knowing it's going to be the square root of that squared and that squared. So it's not 72. Sorry, that's 68. You guys were just laughing at me. You should tell me that. All right. Square root of 68 is my magnitude. Okay? I was actually watching another teacher's video online a couple days ago, and I was like, can't remember how to do, I can't remember what it was, dot product or whatever. And then I saw the teacher mess up, and I was like, ha! But I do it all the time myself. So their answer was supposed to be square root of 34, and they were writing 34 everywhere. It's like, it's a square root of 34. Anyway, okay, so square root of 68 is my, what was that again? Magnitude. That is the hypotenuse, yes, and it's the magnitude. The magnitude is the length of the line, which is the hypotenuse. All right, so smart guy or smart girl, if I have it in 3D, do you get that I might have a vector that's got an x and a y and a z, or an I and a j and a k, and then how are you supposed to find the magnitude when it's like this? All right, I'm going to show you on a little model that I have here. You know that a squared plus b squared equals c squared, right? But when it's in 3D, a squared plus b squared plus c squared will equal d squared. It works. And let me prove it to you. The model that I have has 2, and it says 2. 2 what's? They're decimeters, tenths of meters. They're 10 centimeters for each decimeter. So do you get when it says 2, it really means like 20 centimeters? Okay. Okay, so 2, 2, 1, and 3. And if you actually measure these, I'm going to send it around later with a ruler, it actually measures out to 20, 20, 10, and 30, which I have to scale down to 2, 2, 1, and 3. And I know you know that 2 squared is 4, and 2 squared is 4, and that 4 plus 4 makes 8, plus 1 squared makes 9 total is the same as 3 squared, right? But then, like, why does that work? I'm going to turn it this way. Do you get, if I just look at this triangle, it would be 2 by 2. This hypotenuse here that doesn't exist, you can't see it, but this one would have to be 2 squared, and 2 squared makes 4, and 4 square root of 8. That side that's missing would be the square root of 8. So now I take this other triangle, if I look from this side, that's the square root of 8. Square root of 8 squared, 8, plus 1 squared, 9, would be 3 squared, 9. It works. All right, so I don't want to take forever explaining this. I think you get it, that this is going to be the square root of, to find the magnitude of this, I'm going to do the square root of 2 squared plus 3 squared plus 5 squared. That's all there is to it. So square root of 4 plus 9 plus 25. So square root of 13 and 25 is 38, I think. There we go. I found the magnitude of that vector. Okay. Next, let's say this vector here that I just figured out, its magnitude, or the length of it, is square root of 38. That's a weird number, isn't it? Square root of 25 would be 5, so it's like 6 would be 36, so it's a little more than 6. It's like 6.1 or whatever. What if I wanted to make that vector be 8.2 inches long? Do you get how the sides would get really ugly instead of the sides being nice? The sides were 2, 3, and 5. And it gave me a length of, like, again, this is like 6.2 or whatever. What if I wanted, the problem said, and this is the kind that you would have to be able to do, take that vector and tell me its dimensions. If its length isn't 6.2, or square root of 38, what if its length is 17? Figure out its dimensions. All right, so there's a really slick, easy way to do this. I want you to, again, I'm going to be doing this in the classroom here. I've got this meter stick. Do you know that they're 39 inches long? About. Okay. So imagine that this is our vector, and it happens to be exactly this, 39 inches long approximately. Okay. Vector. But what if I wanted it to be 780 inches long, and it wasn't just a nice simple multiple? Okay. Well, first of all, what you do is you scale the vector down to be only exactly 1 inch or 1 unit long. Because once I have the new vector that's only 1 unit long, do you get if I want it to be 700 units, I can just times by 700? So you first scale your vector down to only be a 1. It's called a unit vector. A vector that's only 1 inch long or 1 unit long in the same direction. That's like this, except only 1 unit long. So how do I take this vector here, which actual magnitude is the square root of 38, and make it be a unit vector? You times it by 1 over, if this thing is root 38, do you get I have to times it by 1 over root 38 to get it to equal 1? What if it was 39 inches long? I'd have to multiply by 1 over 39, right? Get the idea? All right, so simple one. 2, 5. That's a vector. First of all, figure out its magnitude. Go. I'll pause while you do that. I hope you're getting faster at these. You don't have to draw it all out. You just go square root of 4 and 25. Right? Raise your hand if you had square root of 29. Good. So how do I make a unit vector out of it? 1 over root 29. Do you get, I just multiplied it by a number. That's called a scalar. That's a scalar. That's the vector. Together they make a unit vector because I just shrunk my vector's length down to be only 1 unit long. That's what its magnitude is. Now, if I actually wanted to know how much in the I direction is it going to go now, I can take this times this. So it goes 2 over root 29 in the I direction. And I can go this times this to see how far it goes in the J direction. Okay, so that's a unit vector. Now that I made it 1 inch long, or 1 unit long, do you get if I wanted it to be 28 long? It'd be super easy. If I wanted it to be 28 long, I just times it by 28. That's it. All right, great to know. All right, I thought I had those turned off, but apparently not. If I want it to be 28 inches long, I just times it by 28. That's it. Because by doing this, didn't I scale this thing down so it's exactly 1 long? If it's exactly 1 long right now it's super easy to make it any size I want. So if I say I want it to be 50 units long, well, this is 1 unit long, times it by 50. Okay? All right, let's see if you can handle that process. Here is a vector, 3, -8. Yeah, it's going to be a curved line. That's a vector, right? Find the unit vector for it, because that is definitely not 1 unit long right now. Make it 1 unit long, and then I really want it to be 12 units long. No matter how big it is right now, I want it to be 12 units long when you are done. I'll pause while we give that a try. Okay, I decided to give it a name. I'm calling it Z. Do you get that if I'm trying to find this, I'm trying to find the, what's that called again? Magnitude. I'm trying to find the magnitude of Z. And it is square root of 3 squared and 8 squared. Did you figure out that was 7, what was it, 73? All right, square root of 73. Okay, that's the square root of 73. Then, to find a unit vector, I put a 1 over root 73 here because this guy's length was root 73. By multiplying it by that, it'll shrink it down to a length of 1. And then how long did I want it to be? 12. So then I times this, which is currently has a length of 1 by 12, and now it'll be 12 total magnitude, and it's still in the same direction. All right. If I needed to know how far it was in the I direction, I'd go this times this times this. And the J would be that times that times that. Yes?
Could you, multiply it all out and have, the exact...
Yes, that's what I was just saying. If they asked you how far in the I direction is it, it would be 12 times 1 times 3, so it'd be 36 in the I direction. And then how far is it in the J direction? 12 times root 73 times -8. Okay, so there's your unit vector thing. One more thing, and this is super simple. Remember in that formula, does anybody have a short-term memory and remember what the formula is to find? It has a cosine in it. Okay, but that wasn't times. A dot, I know that seems dumb, but it's true. That is not multiplication. It's a dot product. Dot, so A dot B. And that's a multiplication. That's a times. How do you tell the difference? Because it'll be a big fuzzy dot. A dot product. And you have to know this formula. You're the one that's going to be writing the formula down. So just don't confuse yourself to think that it's just multiplying them. All right. And then the last thing is cosine of the angle. And that's how you find the angle between any vectors, is that formula. The only thing I haven't told you is, what the heck's a dot product? I already told you how to find magnitudes. That's easy. You don't even use unit vector in this problem because we don't need a unit vector. Okay. By the way, in case you want a unit vector, it's got a little hat on it. Okay? It's wearing a sombrero or I don't know, some other kind of hat. But that little a with the little hat on it, that meant unit vector. There's no unit vectors in this, but there's dot products. I'll get the excitement over with. It's so simple. If I was going to have two vectors and they were 3, 7, and negative 2, 1, all you do is this times this, and that times that, and then you add them. The multiplication across the top, I totally get you would get, but then you add them because it needs to be just a number when you're done. It's not a vector anymore. And again, like I told you, it doesn't give you anything that I can show you in a picture. It's not like the length of something. It's just a number. All right, so this comes out to negative 6. This is positive 7. What do you get when you put negative 6 with positive 7? 1. All right, so if my two vectors are 3, 7 and negative 2, 1, let's call this guy A and this guy B. I just figured out the dot product of A and B was 1. So all of this over here is just 1 equals. And now can you do the rest of it? You should. You should be able to figure out the magnitude of A pretty quick, the magnitude of B pretty quick, and you'll need a calculator that can do inverse cosine at the end. Grab your calculators. You'll need them for today. I'll pause and grab your calculator. So we got root 58 for the first magnitude, root 5 for the second magnitude, and the dot product, remember, was just 1. So now we have 1 equals root 58, quiet please, root 5 cosine theta. Tell me the next step. Row 1, third person. What's the next step? I'm right here right now.
Okay, multiply square root.
You could do that, yes, that would work. And then you're going to do what?
Do it first cosine, and then you divide it.
You got to divide it by that. So I'm going to just divide it by that. And then how do you finish the deal?
Do inverse cosine.
Inverse cosine of that. And that'll give you your angle. All right? Row 1, person 4. What was it?
I was at grade QDM.
Oh.
86.63.
86.6 degrees. Raise your hand if you had 86.6. Okay, good. All right, that's how you do the angle between two vectors. It's a pretty intense formula, but you guys seem to be able to, you have a short-term memory still. That's good. All right, so let's look at the homework together. I'll pause and we'll get to that page. Okay, so we're going to start on this page, and all it says is find the lengths of these vectors. So again, if I wanted to write this as a column, it'd be 1, 3. The length isn't the length the same as the magnitude. And yes, technically this is called a surd, which I find absurd. Square root of what? Can you do it in your head? I can. 10. Very good. Isn't that the same thing as the magnitude? Yep. All right. So that's all they're asking you to do. They're not super hard. They're incredibly easy, in fact. So those three are just find the magnitude. These are find unit vectors. Remember that part? So let's do the magnitude of it real quick because we're going to need it anyway. What's the magnitude of that guy? Square root of 32. Very good. And if it's the magnitude is the square root of 32, to get the unit vector, I put 1 over square root of 32. There we go. That's the unit vector. Now, do you actually have to multiply that out? No, you can leave it like that because it's cleaner, because you can see the little factor in front. All right, now, if you were asked to give one that was 23 units long, you first make the unit vector, and then you want 23 of them. Right? You know what I'm saying? They didn't ask you for that in this case, but all right. When it has 3 numbers, it's still the same exact process. We talked about how to find the magnitude if there's 3 numbers. 2, -2, -3. Magnitude of that is square root of 2 squared, 2 squared, and 3 squared. Why am I ignoring the negatives? Because we're going to square them anyways. So you got 4, 4, and 9. That's 8 and 9 makes 17. Did you get square root of 17? Good. And then I did not make a unit vector yet. I go 1 over root 17 to get my unit vector. I'm doing too many problems for you, but this is so fun. I don't want to stop. Okay, moving on. This is pretty much just telling you where this vector is. By saying instead of I, J, and K, it's saying north and south and west. Get the idea? It's still just a vector question. It's not incredibly hard. I think we're going to skip number 4. No, wait, that's just like stuff we have to know for the test. So I better leave 4 in there. We're doing 3 and 4. I guess we don't need to do 2 of them, though. I'm going to let you skip B as in banana. So skip that one. Then get to this page. And I don't feel like we need these, so we're going to skip this whole page. Then I'm trying to make the assignment reasonably sized here. And this is reminding you how to do dot products and stuff, but you'll have to do those in the last questions anyway, so we'll skip those also. Wouldn't hurt you to do them, but I'm letting you skip them. And this is the kind where you use that big, hairy, scary formula, which will make you do dot products, and it'll make you do magnitudes. And so at the end, you'll do an inverse cosine. And I want you to just do the top 2. So you may skip this and you may skip this. You know where you can go if you want extra practice problems the night before the test. There's nothing wrong with the problems I crossed out. I just don't need that many. Okay? That keeps it reasonably sized. You may stop at that right there. You don't have to do the rest. Okay? All right. The rest of the time is yours. That's all I got for today.